Thank you for joining me today as we try to prove that the sum from 1 to n of 2 to the I is just 2 to the n plus 1 minus 2. Now as we go through this proof, we're going to use a proof by induction, meaning that we're going to show this is true for n equals 1, and then we're going to assume that this is true for n equals k and prove it's true for n equals k plus 1. In that process, what we get is, because it's true for 1, that implies that it's true for 2, and then 3, and then 4, and then we'll get that the statement is true for all n as natural numbers. Therefore, in order to start this proof, we're going to let n equal 1, and we're going to see what both sides of the equation look like. And so we're going to have our base case is going to be let n equal 1. Then we have that the sum from I equals 1 to 1 of 2 to the I is just equal to 2 to the 1, which is just 2. Now on the other hand, we want to show that it's going to be equal to this if we plug 1 in for n. So I'm going to start off over here and I'm going to say 2 to the 1 plus 1 minus 2 is equal to, well, 2 squared is 4 minus 2 is just 4 minus 2, which indeed is 2. So we get that this statement is true for the case where n equals 1. Alright, now that we've shown the base case for our problem, that is when n is equal to 1, we show the sum from 1 to 1 of 2 to the I is in fact just 2, which is the same as 2 squared minus 4. And so now what we need to do is we need to say, okay, well, let's assume that this is true for the kth case. And now when I assume it's true for the kth case, it looks like I'm assuming that the theorem is always true, but that's not actually what I'm doing. I'm assuming it's true just for this k. And then what I need to do is, based on the fact that it's true for this k, I have to show that that would imply that it's true for the next term, or the k plus 1 term. So our goal in the induction step is to say, okay, well, if it was true for k, let's show it's true for k plus 1. And so we get to assume that the sum from 1 to k of 2 to the I is 2 to the k plus 1 minus 2. And what we have to prove is that the sum from 1 to k plus 1 of 2 to the I is 2 to the k plus 1 minus 2. So now as we go through this, we're going to want to be able to use this to get this out somehow. And so if I'm going to prove that these two are equal, what I'm going to do is I'm going to start off with the left-hand side and somehow manipulate it so that it ends up looking like the right-hand side. So I've tried to give myself a little bit more room, and I've written the sum from 1 to k plus 1 of 2 to the I is equal to, and now hopefully I can say this is equal to a bunch of things, and eventually I want this to pop out so that I know that this is equal to this, which is what we were originally trying to prove. Now, the first step in this process when we're working with sums is to notice that, well, if we add up from 1 to k plus 1, that's the same thing as adding from 1 to k, and then adding in the k plus 1 term. So it's going to help us if we can break it up that way. So I'm going to write this is the sum from 1 to k of 2 to the I, and then I'm going to add in the k plus 1 term, so I'm going to get 2 to the k plus 1. Now the reason why that's going to be helpful is because according to the induction hypothesis, we already know what this is. That is, we assume that our statement was true for this k, so what we can use is we can use this equation up here, and we get that this is equal to 2 to the k plus 1 minus 2 plus 2 to the k plus 1. So now I'm making progress. I've gotten rid of this first piece of the sum. I've written it as equation. I know that I still have to add this piece in. So somehow I'm going to have to simplify this to end up with this. And so having this goal here in mind kind of helps me decide what to do next is, well, I really want 2 to the k plus 1, and I notice that I have 2 to the k plus 1s. So I'm going to combine these instead of saying one of these plus one of these, I'm going to say I have 2 of these. And so I get 2 times 2 to the k plus 1, and then I still have the minus 2 at the end. Now notice that I have the same base. This exponent would be 1, so I would add exponents. So I get 2 to the k plus 1 minus 2 is equal to this term up here. And what we end up with is we just have 2 to the k plus 1 minus 2, which is exactly what we're looking for. And so we have indeed shown that if this is true for the kth term, then it must be true for the k plus 1 term. Now, if we combine that together, what we get is that, well, we already showed it was true for 1, so if we let 1 be k, that means that this is true for 2. Then, if we let 2 be k, that means that this has to be true for 3. And if we continue, we get that the statement has to be true for 4, 5, 6, 7, and it will have to be true for all natural numbers n. Therefore, by induction, we've proven our theorem. Thank you for joining me today as we work through the proof of this theorem. I hope you enjoyed it, and I hope you learned something along the way. If you did, make sure to click that like button and to subscribe to the channel. There's more resources available in the description below, and also check out our other videos.